Yeah, can everyone see my screen? Why can't you see it? Let me check. Okay, so once I go to PowerPoint, can anyone see, everyone see it? So turn off your microphone once I go to PowerPoint. Okay, let me do this. How about now? Someone can turn on your microphone and say that. So I'm using Chrome. I'm not sure if that browser is a problem. You still see arrows. What is that? So I'm now not showing PowerPoint, right? I'm in Canvas. Okay, let me go back to PowerPoint. So asymptotic notations and the two curves 2n and 0.05 and square. So this is what I'm showing now. Now I'm back to the canvas, so you may see some arrows now, but when I go to PowerPoint, you should be able to see only the slide. Is that what everyone is seeing? Going to let me. Okay, good. So please refresh your page. Alright, so now I am in PowerPoint. So refresh your page and you should be able to see it. Okay, so I'm just coming back to check if someone still has any problem. Alright. Okay, so the two functions are 2n and 0.05 and square. So I am plotting them with the n values as n increases, say from 1 to some 100. So these are the values of the two functions. The blue line is the 2n function and the pink curve is the 0.05 n square function. So you can see after a critical value of say 40, so when n is 40, 2n is same as 0.05 n square. 2 times 40 is 80. 40 square times 0.05 is also 80. So at n equals 40, both functions have the same value. Now after n goes above 40, so if n is greater than 40, you can see that the 0.05 n square function starts growing larger than 2n. So we can say for some n greater than equal to 40, this function 2n is always less than or equal to 0.05 n square. Okay, so now after n is 40, if n is greater than or equal to 40, you can say like that. And once n is greater than or equal to 40, the value of 2n will always be less than or equal to this. It won't go above 0.05 n square. So we can say this 0.05 n square function is an upper bound for this 2n function. Okay, so we can say this 2n equals what is called the big O notation of, we can say 0.05 n square because that's our actual function here. But when you write, so this big O is an asymptotic notation indicating kind of like upper bound. So 2n less than or equal to. So any function that is written on the left hand side will be less than or equal to the function that is inside the big O notation. Now when you write a function inside the big O notation, like in this case we want to write 0.05 n square, but we typically omit the coefficient of the function inside the big O notation, and we just say it is n square. Okay, so the degree of that function, which is called the polynomial here, is what that matters. So the degree of this function here is n square, whereas the degree of the function on the left hand side is 1 because it is simply n. So again, you can omit the coefficient of the function on the left hand side and simply say that is n. So n is big O of n square. Okay. Now, so how do you decide when to use a big O notation? So the rule for using big O notation is the degree of the function on the left hand side should be less than or equal to the degree of the function on the right hand side. That is how you decide when to use a big O notation. Okay, so I'm just coming back to see if someone has any problem. So can you see in the slide when I was talking in PowerPoint?
Yes, I can see the slide.
Okay. Not sure if someone still has a problem, but I'm not sure if majority of you are able to see it. I think it's some problem on your side. You have to fix it.
I had to leave the conference and come back in for it to pop up on my screen.
Okay, so if anyone is not seeing yet, please follow the whatever that person said. Log out and then log in again to Canvas. I'm using Chrome.
Mine messed up earlier and I had to close Chrome altogether and reopen it before it would work correctly.
Okay, great. Alright, so let me go back to PowerPoint. Okay, so if I have a function say this, so typically when you work with problems, you won't be given two functions. So one will come across situations like this. We'll analyze the time complexity of algorithms and we will come up with some function which could be a polynomial. So for example, after we analyze the time complexity, let us say this is the polynomial I'm getting, 2n square plus 3n plus 5. So how do we write this using a big O notation? So the kind of intermediate steps that will follow is we will omit the lower order terms. So in this function there are three terms. There's a 5, there's a 3n and there's a 2n square. So among these three terms, as n increases, 5 is a constant, its value is not going to increase. 3n, of course, its value will increase, and then you have 2n square whose values will also increase. As n grows to infinity, as n grows larger, even 3n becomes less dominant. 2n square is the most dominant function. So what we'll do is we'll retain the most dominating term in this function, which is 2n square. And for using the big O, what goes inside big O, the degree of that polynomial, the function should be what? Greater than or equal to the degree of the polynomial on the left hand side. So in this case, we are going to say 2n square plus 3n plus 5 is simply 2n square as n goes to infinity. And now we can just say it is big O of 2n square or omit the coefficient and simply say it is big O of n square. So once we say it, we can say it's big O of n square, we can say anything big O of n cube or n to the power 4, anything, because the rule is the function that goes on the left hand side, the degree of that function, which is 2, should be less than or equal to the function on the right hand side of the big O, inside the big O notation. So what goes inside the big O notation is the big guy, which means its degree should be greater than or equal to the function on the left hand side. So always remember this curve like this. So if this is the function on the left hand side 2n, and this is a function inside the big O notation, the degree of the left hand side function should be less than or equal to what goes inside the big O notation. So we can say the same function 2n square plus 3n plus 5 is big O of n cube or n to the power 4. We could even have say n to the power 2.1 or 2.2 or anything inside the big O notation, as long as the degree of the function on the left hand side is less than or equal to the function on the degree of the function on the right hand side. So that's why I say it's a upper bound as well as it's a loose upper bound. So why I say it's a loose upper bound is because there's no fixed value we can have for a function inside the big O notation. So for a given function f of n on your left hand side, there's no particular upper bound you can come up with for the function using the big O notation. Okay, so you can have only a loose bound. Now if we have to have a tight bound for a function f of n, so we want to find out what is the exact rate at which the function on the left hand side grows. So when I say exact rate, it means the same rate. So for that, do the same steps, omit the lower order terms and find the most dominating term, which is 2n squared, skip the coefficient of the term, and instead of using a big O notation, use the theta notation. So we can say this 2n squared plus 3n plus 5 is theta of n squared. So that means the degree of the function on the left hand side of this f of n should be the same as the degree of the function on the right hand side, which is this g of n. So that means we cannot say 2n squared plus 3n plus 5 is theta of n cube, because the degree of the function f of n on the left hand side is less than the degree on the function on the right hand side on inside theta notation. So for theta notation, what goes inside the degree of this polynomial should be same as the degree of the polynomial that you have on the left hand side for f of n. Okay, so when you say f of n equals some theta of g of n, the two functions should grow at the same rate, which means in terms of degree of the polynomials, it should be the same degree. Okay, so that's why we say this theta notation is like a tight bound. It gives you what is the rate at which the function really grows. So when you have say a linear function like 2n, we can say 2n is theta of n. Now the function g of n that you put inside theta notation could have some coefficients like n or 5n or anything, but again you do not write those coefficients inside the theta notation also like big O notation. So any asymptotic notation, you don't write any coefficient or more than one term, you always include the most dominating term, and in this case we can simply say 2n is theta of n. Okay, and so the degree of the polynomial on the left hand side, which is 1, is same as the degree of the polynomial on the right hand side, which is also 1. Okay, so that is again the difference between the big O and theta. So for big O, let me come back and see if somebody has any question. Okay, so for big O, it is a loose bound, so as long as the function that goes inside the big O notation has the same degree or a larger degree than the function on the left hand side, we can use the big O. So always think the big guy, the upper bound. For theta, it should be the same degree, same rate. Okay, so it looks like there is some relation between the two notations, and there is some difference also. So let us see what is the relation, what's the difference between the two notations. Now if you go back to what we just saw, we can say, let me pull out here, I have it here too. We can say, for example, 5n square plus 7n plus 2 is theta of n square, because again the degree on the left hand side is 2, on the degree of the function inside the theta notation is also 2. So same degree, we can use theta notation. But by definition of big O, we can also say 5n square plus 7n plus 2 is big O of n square, because it still satisfies the definition. The degree of the function f of n on the left hand side should be less than or equal to what goes inside the big O notation. So it could be equal to or could be less than. So we could have 2, that means equal to. If you want to apply the less than part of the definition, you could have 2.1, 2.2 or 3 or 4 inside the big O notation. So that equal to part of the definition is what is common between the theta and the big O notation. So that means if f of n equals some theta of g of n, f of n is also big O of that g of n. So that's what I have here. So f of n is theta of n square. We can also say f of n is big O of that n square, that g of n. So we can simply say theta implies big O. So if some function f of n is theta of g of n, it's automatically also true that f of n is also the big O of the same function g of n. Now how about the reverse? If some f of n is big O of g of n, can we say f of n is also theta of g of n? The answer is it need not be. It depends on what are the two functions f of n and g of n. So for example, if I say phi n square plus 7n plus 2 is big O of n cube, that is right because it satisfies the definition of big O. The function degree of the function f of n is 2 is less than the degree of the function g of n, which is inside the big O notation. So as long as the degree of the function f of n on the left hand side is less than or equal to the function of the degree of the function inside the big O notation, we can use the big O notation. So it's an upper bound now. So now since f of n is big O of g of n, can we say phi n square plus 7n plus 2 is theta of n cube? We cannot say it is theta of n cube because for theta the degree should be the same for f of n as well as g of n inside the theta notation. So that is where the difference is. Similarly, if I say phi n square plus 7n plus 2 is big O of n to the power 4, that is possible. But we cannot say phi n square plus 7n plus 2 is theta of n to the power 4 because the degree is 2 for f of n, whereas the degree of the function inside theta is 4. We cannot say that. That's why I say not possible, not equal to. So, but on the other hand, if I am given that phi n square plus 7n plus 2 is big O of n square, so if the function phi n square plus n plus 2 is big O of n square, we can say it is theta of n square. So it's not that always if f of n is big O of g of n, f of n is not equal to theta of g of n. It depends on the two functions. So if the two functions are the same degree, then we can say if f of n is the big O of g of n, it is also equal to theta of g of n. But if the function inside the big O notation has a larger degree, we cannot say f of n is theta of g of n. So somebody is having their microphone on, please turn it off. Okay. All right. So let's see one more example just to make sure everyone gets it now before we proceed. So let us say I have 4n cube plus 3n plus 5. Now I can say how to come up with asymptotic notation. Again, omit the lower order terms. So omit 5 and 3n. 4n cube is the most dominating term as n grows larger. So once you decide that, again skip the coefficient of the most dominating term, which is 4. So you're simply left with n cube. So now I can say it is big O of n cube because by definition the degree of f of n should be less than or equal to what is inside the big O notation, which is 3. So equal to. Now applying the less than part of the definition, I can say it is big O of n to the power 4 or big O of n to the power 3.5, etc. anything. So if I ask someone in an exam for what is the big O, how can you express this function using a big O notation, someone can come up with big O of n cube, someone else can come up with big O of n to the power 4, so there's no particular answer. So this is like a loose upper bound. Okay. Whereas if I ask you to represent this using a theta notation, there's only one answer because they should have the same growth rate. So 4n cube, skip the coefficient and simply say it is theta of n cube. So that's the way you decide which notation to use. If I want you to use a theta notation, it has to be the same rate. If I want you to use a big O notation, you could use the same rate or a larger rate, which is like 3 or more than 3 in this case. Okay. So now the difference between the two, if I say 4n cube plus 3n plus 5 is theta of n cube, I can also say it is big O of n cube. Okay. But if I say 4n cube plus m plus big O of n to the power 4, yes, it is true, it's possible. We cannot say it is theta of n to the power 4 because they have the function set theta has a larger degree, which is not possible to write. So that's the relation. Okay. If 4n cube plus n plus 5 is big O of n cube, the same rate as f of n and g of n, so we can say f of n is also theta of g of n. So that's why theta implies big O, because theta means same rate. So big O, we have two parts in the definition, one is less than and the other is equal to. So if it's equal to, we can say it is theta implies big O. But if it is less than, we cannot say big O implies theta. So that's why I say big O need not imply theta. It depends on what it is. If this is what you write as big O notation, we can say it is also theta. If this is what you write as a big O notation, because it is 4 and this is 3 on the left hand side, we cannot say that is equal to theta. Okay. So this is what you need to know about the two asymptotic notations. Let me come back to Canvas. Any question? So if someone logged in recently, log out and refresh your screen, open Chrome again, refresh your screen and log into Canvas, and you should be able to see it. Okay, so if no questions, let us continue. Let me just save this video.